Hi class, this is an example problem for Unit 3.3. In Unit 3.3, we expand upon what we learned in the previous two, 3.1 and 3.2, but we just take it to the third dimension. So I picked problem 3-55 from the book, 13th edition, and it looks like this. So just let me take a look at that to try to understand what I'm trying to draw. Drawing on a board in 3D is always a little bit challenging, but done my best here. So what we have is essentially, we have this crate and it's being supported at point A. And at point A, there is also a cable AB that is supporting it, a cable AC that is supporting it, and then the strut, this rigid member from O to A that is also supported. So this is my X direction, Y direction, and my Z direction. I have all the dimensions labeled. And what we're told is that the tensions and the maximum tension that cables AC and AB can support is 300 pounds. So if we find that the tension in either of those exceeds 300 pounds, that tells us that the cable would break at that point. So what we're asked to find is the maximum weight of the crate that can be supported at point A. And we're also asked to find the force in the strut AO that develops at that point. So this is I like this problem because it's going to demonstrate some good points about anytime we have a problem like this where it says the maximum that these things can support is such and such pounds. Find which one breaks first, or find the maximum force they can support. It can be a little tricky, and this gives us an example to kind of talk through how we can solve this. So in this particular case, right? So we're just trying to find the tensions that develop and the force and strut AO. So solution then. So first thing I'm going to do, we have all these positions. I need some position vectors, and namely, I want the position vector. I need to find the position vector that describes the direction of AC, AB, and AO. I need those three. So first, let me draw. I guess maybe let me take a step back and draw the free body diagram at point A. Point A is where all my forces of interest are acting. So I'm going to start there. So at point A, we have a tension AC, we have a tension AV, we have a compression. We call this force OA, and then there's the weight of the crate, which is we don't know what that is yet, but we know that this has to. So just like before, we draw a free body diagram, and only this time it's in 3D, and we know that summation of those must equal 0. So let me find my unit vector. So with unit vectors, I'm going to start with unit vector AC. Right, so we just take our position vectors and we divide them by the magnitude. So AC, I'm going from A to C. So if I'm going from there and I'm walking in the X direction, so with position vectors, I like to think of it like giving directions, where you can only give directions in terms of going in the X direction, Y direction, or Z direction. Right, just like with on your GPS, right? It's going to tell you go north for 2 miles and then go west for 3 miles. That's how you get there, right? Because normally when you're driving in a car, you can't just cut through neighborhood blocks, right? There are houses there. You have to go kind of in orthogonal directions. So that's what the position vector is. It's a map that tells you how to go from your starting point to your. So if I'm telling somebody how to get from point A to point C, I'm going to tell them you're going to go 2 feet in the X direction. So the unit vector for AC is going to be the position vector AC divided by its magnitude. And the position vector, so to get the position vector, I tell them to go 2 feet in the X direction. I'm going to tell them to go -6 feet in the Y direction. I'm going to tell them to go, okay, so this one starts at 2.5 in the Z. It's going to go all the way up to 5.5 in the Z. So that's a difference of +3 in the z direction. And the magnitude, of course, is just the square root of the sum of the squares. 2 squared, 6 squared, 3 squared, and I end up with that is u7, so I get 2i minus 6j plus 3k divided by 7. Okay, so let's keep going. UAB, I'm trying to tell somebody how to get from point A to point B. I'm going to tell them. Similarly, they're going to go now -2 in the x direction, -6 in the j direction, and let's see, we started at 2.5, we go up to 4. That's a difference of 1.5. Z direction, squared plus 6 squared plus 1.5 squared. And when we figure that out, it has 926.5. And finally, AO it's the same as position vector AO and magnitude. AO has no change in x, so it's going to be 0i and -6 k and minus 2.5 k, or the square root of 0 squared plus 6 squared plus 2.5 squared, which ends up giving me 0, -6, -2.5 divided by 6.5. Okay, so I have these 3 unit vectors. That right there is the majority of the work in this case. So now that I have those, I can now look at kind of our main equations, or semi-forces in x and y. I'm going to start with semi-forces in x. And the reason I'm going to do x is because x only includes our tensions. Everything else has no x component. So that lets me isolate a few things and get me so the tension in those cables in relationship to each other. And so when I do that, semi-forces in x equals 0. 0 is going to equal TAC. And now, right, so I'm going to be looking for basically, I can just take the x part of my unit vector and multiply it to get my x component of that. So TAC 2/7 minus TAE 2 divided by 6.5, right? Got that. And so if I do a little bit of rearranging, I get that TAC is equal to 7 divided by 6.5 TAC. Okay, so what does this tell me? Looking at this, I can say that TAC is always going to be larger than TAB. Now that's important because that tells me if the maximum that either of those can support is 300, I know that TAC will hit 300 pounds before TAB hits 300 pounds, right? There's a fixed relationship between them based on the geometry. And so now I know that TAC must be 300. And if I plug 300 in for TAC, I can solve for TAB. So when I do that, I can get that TAC, right, equals 300 by inspection. And therefore, TAB will equal 278.57. Now those weren't the answers I was being asked for, right? I'm being asked to find what W is. So let's find my other forces. Before I can really find W, I kind of want to, so I really have two unknowns still. FAO and W. So I have two equations left I can use. I have sum of forces in X, or sorry, sum of forces in Y and sum of forces in Z. Both FAO and W have a Z component, but only FAO has a Y component. So if I do my sum of forces in Y, I can isolate that unknown and solve for it. And I'm running out of space quickly. Maybe I can fit it all. This is bad formatting. Hopefully you would do it nice and clean down your column. I'm going to jump up here. I think I can fit it the rest of it. Sum of forces in Y equals 0. So what's in 0? Okay, so in Y, I have TAC, TAB, and FOA all have a Y component. W has no Y component. So TAC, let's look at that. It's going to be minus 300. That's the magnitude. And the Y part of TAC, so 6/7. Then minus TAB, 278.57, and its Y component is, you can find it by timesing that by 6 divided by 6.5. And then we have FOA, which we don't know, but it's going to be multiplied by also, well, in this case, we actually, because it's going, we're defining it as going this way. So that's going to be positive 6 divided by 6.5. So when we defined OA, we said it's negative, but really we're finding F. So we found the unit vector for UAO, but we're finding the force OA. So the signs just flip because it's going the opposite direction. Okay, so we got this. We can simplify the math down, and we end up with F OA equal I'm just going to skip math steps. Please show your work in your years. I'm just trying to conserve space. 557.14 pounds. So that is the force that develops in the strut. And now we only have one unknown left, which is W. And we have one equation left, which is the sum of forces in Z. And so there's going to include the Z component of everything. So TAC, its Z component is 300 times 3/7. TAB, its Z component is 278.57 times 1.5 divided by 6.5. And FOA, its Z component is 557.14 times 2.5 divided by 6.5. And finally, all minus W. So we can do all that math. And what we end up is W equals 406. So those are my answers. So yeah, with 3D problems like this, really just the same as the 2Ds, just now we have three equations, sum of forces in X, Y, and Z that we can use, which means we can solve up to three unknowns. When you have a problem like this, where it asks you to find the maximum force that can be supported before something breaks, in the best case scenario, right, you get a case like this where you can directly compare them, and you can know, okay, this one's definitely going to break first because it's more than one times what the other one is. Sometimes you might just have to make a guess and just plug a value in for one of them. You might just say, I want to plug in 300 for TAB, see what comes out, and then if the other one is larger than that, you guess wrong, and just plug plug the value in for the other one. But I know those kinds of questions can be tricky. So hopefully that is helpful in understanding some of the problems from Unit 3.3.